Okay, so good evening everyone. Welcome to week 8 of this tutorial session. Am I audible to everyone?
Yes, ma'am.
Okay, so this week you must have gone through the lectures covering control design, frequency response, and state space model. So in control design, you must have gone through lectures where you were designing the proportional gain based on specific performance characteristics. And then in frequency response, you must have seen how the steady state response will be in the case of sinusoidal input, and then how to get to state space model of the system starting from the transfer function, or how to convert a model from state space to transfer function or vice versa. So we will be solving problems based on these topics. Before that, in the previous week, I left this question for all of you to try. So in this question, we have open loop poles of a third order unity feedback system which are located at 0, -1 and -2, and the frequency corresponding to the point where the root locus of system transits to unstable region is equal to the value of gain k. Okay, and then we are introducing a 0 at the location -3 in the open loop transfer function. Then which among the following four options is true? So if any one of you have not joined the previous session, you can try this. You can try this now, then I will solve it for you. All of you are able to solve the assignment problems of this course, which is uploaded in your NPTEL.
Yes, ma'am.
Okay, so let's try to solve this problem. Okay. Since we have open loop poles located at 0, -1 and -2, so let's try to draw the root locus for this. So this one is the real part and this one is the imaginary axis. And the poles are located at 0, -1 and -2. So this is 0, this is -1 and this is -2. Okay, now can you guess where on the real part the root locus will lie? The real axis. So if you see on the right, we have no poles or open loop zeros. So this part will not lie in the root locus. And if you see this real part from -1 to 0, will it lie in the root locus? So if you choose any test point SP,
Yes.
then yes. So when you look on the right, you have one open loop pole which is odd, that is 1. So this real part will lie in the root locus. And what about the third case from -2 to -1?
Not like.
So this will not lie, but this part will lie because we have on this right odd number of poles. Okay, fine. And what can we say about the asymptotes? How many asymptotes will be there? N minus m, but m is 0, so it will be equal to n, which is 3 in this case. Okay, and what will be the angle of asymptotes? So it is 180 and minus m. So n equals to 3, so it will be the odd multiple of 60 degree. So it will be 60, and then it will be 180 degree, and then 4 plus 1 5, it will be 300 degree. No, the last one will be is so 4 plus 1 5, 185 the what will be the third angle? 60 into 5 is 300 degree. Yes. Okay, so these will be the angle of asymptotes, and from here you can also guess that since we have no open loop zeros, then this one will extend to minus infinity. So this asymptote is making an angle of 180 degree, and from these two poles we will break away. We can guess it like this, because to make an asymptote of 60 degree and 300 degree with these two poles location, it must break away from here, then it will cross this axis and go to infinity. Okay, now in this uh, open loop transfer function, you are introducing a 0 which is at minus 3, and we have one another information that this transits to the unstable region at frequency equals to k. So what is happening? So at this point it is crossing the imaginary axis and it is going to unstable region, because this RHP is the unstable region. So it is going to unstable region, and this frequency omega is equal to k. Okay, this much information we have. And now we are introducing a 0 at minus 3 in this open loop transfer function. Okay, now let's see how this root locus will change if we introduce a 0. Now can you try plotting the root locus when you have these three poles, and in addition you have a 0 at the location minus 3? Try to draw the root locus. So we have these three open loop poles, and in addition to that we have a 0 at the location minus 3. Now what will happen? So first let's try to see which part will lie in the root locus. So again we will have this part in the root locus and then this part. Okay, and number of asymptotes in this case will be Now we have 1 0 also, so n minus m will be 3 minus n, which is equal to 2. So we have two asymptote, and that is obvious because in earlier example, in earlier case we have three open loop poles and no zeros, so all three asymptotes, all these three branches will converge to infinity because we have no zero to terminate on. But in this case, since we have one open loop 0, so one of the branch will converge to this open loop 0 and the other two will terminate to infinity. So that's why earlier we had three asymptotes, but now we have only two asymptotes because only two branches will be going to infinity in this case, and the another will terminate to the open loop 0. And what will be the angle of asymptotes? Again we have, and in this case we have n minus m equals to 2, so we will have odd multiples of 90 degree, so it will be 90 degree and another will be 270 degree. Okay, now so from here you can guess that since from this open loop pole this branch will converge to this open loop 0, so the asymptotes which is having angle of 90 degree and 270 degree, these will for sure originate from here, from the open loop poles. So our root locus will go to infinity by making an angle of 90 degree from one pole and 270 degree from the another. So what do you think? Are you going to cross the imaginary axis for any value of k? No, we are not going to cross because the angle of asymptotes are 90 degrees, right? So if you increase k, you will never going to cross this imaginary axis, right? And if you are not crossing the imaginary axis, means you are not going to this RHP. You are not going to right hand side of this imaginary axis, means you will not have any positive closed loop poles, right? Then which option you can choose among these four? Which one is the correct option? So is there any point on the root locus where the system will transit to unstable region? No, we have no frequency such that our root locus will transit to unstable region. So the root locus will never transit to unstable region. Is it clear to everyone?
No, ma'am.
Okay. And about one more question we left. So yeah, this one in this question we found out the angle of asymptote at 0 degree. So the angle 0 degree means, it was very obvious, but I don't know why I got confused in the last session. So 0 degree means you are on the parallel to positive real axis, right? So the correct answer is positive real axis as the only asymptote. Okay, now let's start today's session, today's questions. Okay, you have open loop transfer function of a negative feedback closed loop system, which is given by k by s square plus 5s, and k is a non-negative real valued parameter. You have to identify the value of k for system to be stable. So these type of problems we have solved many times, and you can easily guess this time. So you have open loop transfer function gs into hs is given as k divided by s square plus 5s. So what will be the closed loop transfer function? It will be k divided by s square plus 5s plus k. For what value of k the roots will be on the LHP?
Positive values.
We have to choose k greater than 0. Okay, so that's the easy one. And now again we want the closed loop poles to be such that it will be an underdamped second order system. Then what k should satisfy this condition? We want the system to behave like an underdamped second order system. Now let me write the closed loop transfer function. It was k divided by s square plus 5s plus k. Okay. For underdamped system, what is the range of zeta? It should lie between 0 to 1. And from here you can identify your 2 zeta n equals to 5 and omega n square equals to k. So omega n is nothing but under root of k. And then from here, if you calculate zeta, it will be 5 by 2 omega n, which is equal to 5 by 2 under root k, right? And this zeta, which means this 5 by 2 under root k should be between 0 and 1. Then find the range of k.
Greater than 6.25.
Okay, let's see. Okay, so 5 by 2 should be less than root k, or k should be greater than 25 by 4, which is equal to 6.25. Okay, so k should be greater than 6.25. Okay, now in third problem, for this underdamped second order system, which is which option is true? If you have k greater than 6.25, which means your system is underdamped, then which among these four options is correct? So first you need to understand the settling time. So what is the formula of settling time? It is equal to 4 by zeta omega n. Okay. for this characteristics for this closed loop transfer function, you have 2 zeta omega n equals to 5. Let's see. So you have 2 zeta omega n equals to 5. Then your zeta omega n equals to 5 by 2. Now put this here. What settling time you will get? So this will be equal to this 8 by 5, which is equal to 1.6 second. Which option is correct? You have settling time of 1.6 second.
First option.
Again, you want the maximum peak overshoot to be less than 10%. Identify the range of K. Okay, let's see. We want the maximum peak overshoot in percentage we have should be less than 10%. And what is the expression for maximum peak overshoot? It is equal to e to the minus pi zeta a under root 1 minus zeta square, and it should be less than equal to 0.1 if we remove the percentage. First solve for zeta, then put the value of zeta from above that we have already calculated, which is 5 by 2 under root k. Then you will get the expression for k. Okay, if you take ln both sides, you will get zeta by under root 1 minus zeta will be less than equal to ln 0.1. And what is ln of 0.1?
minus 2.3025.
Okay, so this is equal to minus 2.302. Put the value of
5.
pi and solve for zeta. So if you cancel a negative sign, your expression will reverse. So it should be greater than equal to 2.302. Any one of you solved? Or you can directly put value of zeta, which is 5 by 2 under root k divided by under root 1 minus 25 by 4k should be greater than equal to 2.302. Solve for k. So if you solve, you will get k less than 17.8. Okay. And from earlier uh, condition, we got k to be greater than 6.25. So the range of k should be between 6.25 and 7.8. So these questions are just formula based, and you need to be fast in calculation for such type of questions. Okay. Which one of the following statements is true about the locus of the closed loop poles of this problem, which was, let me write the closed loop, let me write the open loop transfer function. It was k divided by s square plus 5s, I think. Yes, s square plus 5s. Okay, now comment on the root locus. Let's try to draw it. So we have open loop poles at 0 and the another is at -5. Okay. Now on which part of root locus, which part of real axis the root locus will lie? This middle one, because if you look right from here, you have only one pole. And then how my root locus will evolve? So for that, how many asymptotes will be having?
Two.
We have two asymptotes. And what are the angle of asymptotes?
90 and 270.
Divided by 2, so it will be 90 degree and 270 degree. And now from here you can guess that you will start from these open loop poles and then you will break from here by an angle of 90 degree and 270 degree to infinity, because you have no open loop 0, so you will go to infinity this way as you increase k. Then which option is correct?
And first,
So the root locus will always lie on the left half of the complex plane for k greater than 0. For such questions, always check the value of k also, because if you have k less than 0, then your answer will change. So sometimes in gate you will see that they twist the question like this way, and if you don't check the sign of k, you will tick the wrong option. Okay. You have a second order system, and how many state variables is required to express it into state space? So what is the order of um, differential equation here?
Second order.
So you have y double dot minus 4y dot minus 5y equals to 2u. So y double dot means how many times we are differentiating y? We are differentiating it 2 times. Okay. So the order of differential equation is equal to the number of state variables. So in this case, since the order is 2, so we will need 2 state variables that will completely explain the behavior of this system. Okay. And what is the state matrix? So this was your differential equation. Now develop the state matrix for this differential equation. So how we choose the state variables? So we pick one state as y and another state as y dot. Okay. And then if you do x1 dot, what you will get? Y dot, and y dot is nothing but x2. And if you do x2 dot, what you will get? You will get x y double dot, which is nothing but, from here you can solve, y double dot is 2u plus 4y dot plus 5y, and your 4y dot is equal to x2 and y is equal to x1, and then you have the control with coefficient 2. So x2 dot will be equal to, and this is nothing but x2 dot, it will be equal to 5x1 plus 4x2 plus 2u. Now from here, can you develop the state transition matrix by seeing these two expressions? You have expressions for x1 dot and x2 dot. Now you have to develop the state matrix. So your state matrix is nothing but this representation in the matrix form. Now how can you write it into matrix form? So what will be the entries into matrix? So we have x1 dot and this is equal to x2, and here we have coefficient of x1 as 0, so this is 0, and coefficient of x2 is 1. Okay. What about x2 dot? We have coefficient of x1 as 5 and coefficient of x2 as 4, and in x1 dot we have also no coefficient of control, so this is 0, and here we have coefficient of u as 2. Okay. So this will be the state space representation of this differential equation. Okay. Now what is the state matrix? Which matrix is called the state matrix in this representation?
And the square matrix.
So yes, so this matrix is called A in general, and this is the matrix B. So this is the standard representation, and so the answer is 0, 1, 5, 4. Okay. Calculate the eigenvalues of the state matrix. So your state matrix was 0, 1, 5, 4. Calculate its eigenvalues. Okay, how we calculate the eigenvalues of any matrix? We solve the expression, um, you can write it as lambda. So lambda I minus a, you take its determinant and you solve it for 0. Okay. Now what is the identity matrix? Because we have 2 cross 2 matrix, so you have to take the identity matrix of same dimension. Identity means diagonal elements are 1. Okay, so you multiply this with lambda, so lambda is nothing but lambda times of 1, and you subtract your matrix, which is 0 1 5 4. Okay, so what you will get lambda minus 1 minus 5 and lambda minus 4. What is the determinant of this matrix? So to calculate the determinant, you multiply these cross terms and take the and subtract. So it is, take its determinant, it is equal to lambda into lambda minus 4 and minus of, so these minus minus will be plus, so it is just minus 5, and this equals to 0. So you have the characteristic equation as lambda square minus 4 lambda minus 5 equals to 0. What will be the values of lambda?
In 5 and minus 1.
5 and minus 1.
5 and minus 1. Okay. So lambda will be equal to 5 and minus 1. So option A. Okay. What is the input vector of the state space realization of the problem corresponding to the state matrix obtained? So what is the input vector? We have already calculated it. This is our input vector, right?
Yes, ma'am.
No? This is the last option. Okay. Now the input vector, the output vector of the state space realization of problem 6 corresponding to the state matrix obtained in problem 7 is, you have to identify the output vector. Output vector. What is the output of this problem? What do you mean by output? Which state variable is the output?
On the left hand side vector.
No, C. So you have this differential equation given in your problem where your input is u and your output is y. Okay, so this is your input and this is your output variable, right? Y is your output,
Okay,
and
ma'am.
the system is governed by this differential equation, so the output and input follows this differential equation. So now can you answer which variable is the output in our case? Which variable we have assigned as the output?
X1.
It is x1. So if you want to write it in vector form, so y is x1. What are the coefficients? We can write it as 1 x1 plus 0 x2. Okay. So in vector form, what it will be? It will be 1 0 x1 x2. Can I write y like this?
Yes, ma'am.
Yes. So what is your output vector now?
Second option 1 0.
Second option. Yes. Okay. So it is equal to 1 0. Now from the state space realization, find out the transfer function. Let me write the state space. So your x1 dot x2 dot was equal to 0, sorry, 1 5 4 x1 x2 plus 0 2 u. This was your state space realization. From here, find out the transfer function. You can find out the transfer function from the differential equation itself. But how, if the differential equation is not given, how we find out the transfer function if the state space model is given to us?
Ma'am, the previous question is not clear.
This one,
Yes, ma'am.
which part is not clear?
The, the output vector. Has-
So are you able to identify what is the output in this case first? Why are we taking y as output? Is that clear to you?
No, ma'am. There is confusion.
Okay. So here you are given a differential equation, right? Which is this one. And this differential equation is with respect to what? You have the variable y and you have the variable u. Okay. And in this variable, you are able to identify as the input. Okay. And what is y? Y is the variable of interest. Variable of interest means what? This is our output, because this complete expression is with respect to y. These y dot and y double dot are used to represent the system which is governed by this differential equation. But the system
Yes, ma'am.
output is what? System output is y, and it is governed by this law, right? So first we have identified the output, which is nothing but y. And then from here, since our output is y, we have assigned it the variable x1. So this is in general the rule. We take y as x1 and its derivative as x2. Okay. For second order differential equation in general,
Yes.
we take this form. And then since we have y as x1, we can represent it as 1x1 plus 0x2. So the vector takes this form. Because when you expand it, what you will get? You will get just x1. Okay. Is it clear?
Yes, ma'am. But it is a row vector, ma'am, and in option it is given as
Yes, it
column
is.
vector.
Yes, when you have uh, since all the options are in the column vector form, right? So in vector in general, what we say, we have elements in terms of matrix. Okay. But if you have an option where you have a row vector as well, so in that case you will tick that option. But since all are given all are given in terms of column vector, so you need not to worry about that. But if you were asked about the matrix C, then you must have tick the option 1 0.
Okay, sir. Clear, clear, ma'am.
Okay. Okay, find out the transfer function. Okay, anyone of you calculated? So, how we transform the model from state space to transfer function? We have to do nothing but we have the expression for that, and which is derived by doing just the Laplace transform of this one. Okay, if you do the Laplace transform and put initial condition of x1 and x2 to 0, and then if you find the ratio x1 by u in Laplace domain, you will get c times of si minus a inverse b plus d. So this expression you have for converting state space to transfer function. C matrix we know it was, we have calculated it was 1 0 1 0. A we already know from here, and B was control matrix we already know. Where is it? Yes, input vector it is 0 2. And what is D? Is there any D? So if we represent it in standard form, ax plus bu and y equals to cx plus du, and y was x1, so x1 was nothing but 1 0 x, and there is no control in x1, so it was 0, so our d is 0. Okay, there is no element in that, so it is 0 0. Okay, so let's calculate si minus a first. So this will be s. If you multiply s with identity, you will get s, and you have to subtract your state matrix. You will get s minus 1 minus 4 and s minus 4. Okay, and then you have to take its inverse. How to take the inverse of a 2 cross 2 matrix? So you can remember this. You can solve it using adjoint and dividing with determinant, but there is a shorthand rule. What you do, you swap the diagonal elements and change the sign of diagonal elements. So what you will get, if we swap the diagonal elements, we'll have s minus 4 and s, and if we change the sign of diagonal elements of diagonal elements, it will be 1 and 5. Okay, so this will be the inverse, and then also we have to divide it with the determinant. So determinant will be s into s minus 4 minus 5. Okay, so this is the inverse of si minus a. Next what we have to do, oops, what happened? Next what we have to do, we have to multiply it with c. So if we do c times of si minus a inverse, it is 1 0 s minus 4 1 5 s, and in divide we have s square minus 4s minus 5. So it will be, so this is your 1 cross 2 matrix and this is 2 cross 2 matrix. So your resultant matrix will be of 1 cross 2. Okay, and your elements will be, so first you take this and multiply with first row, so you will get s minus 4, and Again you take this row and multiply with this column, you will get 1. Okay, so we have this expression. Now we have to multiply all this with b. So s square minus 4s minus 5, s minus 4 1, and your b was 0 2 0 2. So this matrix is 1 cross 2 and this is 2 cross 1, so your resultant will be 1 cross 1, which is 1 by s square minus 4s minus 5. So multiply this with this element is 0, so you will get 2 only. So your transfer function is nothing but 2 divided by s square minus 4s minus 5. Are you able to follow this?
Yes, ma'am.
So your correct option is third one. Okay, let's move to next problem. So you have an LTI system and you have provided a sinusoidal input and the frequency of the input is 20 hertz, and then you have calculated the steady state output with this input. Then what will be the frequency of the steady state response?
20 hertz. 20 hertz, ma'am.
20 hertz, yes, correct. Why? Because if you have a system, okay, this is your input and this is your output. So when you provide a sinusoidal input which is having some magnitude and phase, then what happens to your output? Your output is scaled by this magnitude which is at this frequency. You can write omega or phi, that is same. So let's call at omega, at frequency omega. So your output will be scaled by this magnitude, and then uh, your frequency will be same as omega, right? And there is a phase shift by what value? Angle of the system at the frequency omega. So in this question we have provided input of frequency 20 hertz. So the output at steady state will be having the frequency equal to 20 hertz only. But there will be a phase shift, but we are not asked about any phases, so the frequency is just 20 hertz. Now you have a transfer function of the plant given as s plus 2 divided by s plus 1, and the magnitude of the sinusoidal transfer function at an angular frequency of 1 radian per second is. So you have provided sinusoidal transfer function as input to the system, and this input has frequency 1. So okay, no, there is no input output thing. You just have to calculate the magnitude of this transfer function at angular frequency of 1 radian per second. So just put omega equals to 1, put s equals to j omega, and then put omega equals to 1 and find its magnitude. we are given transfer function as s plus 2 divided by s plus 1. In frequency domain, we can put s equals to j omega plus 1, and then you have to calculate its magnitude. So what is the magnitude of numerator? It will be nothing but
Root
omega
5.
square plus
Under
1. Yes, and for denominator we have omega square plus 1. And at which frequency we have to calculate? 1 radian per second. So calculate this for omega equals to 1. So it will be under root 5 divided by under root
under root 2.
2. What value will get?
1.5811.
Yes, so that means first option, right? Okay. And also calculate its phase. So for this one, we need to calculate the angle of g of s at omega equals to 1. So what it will be? It is nothing but, so let's first write, okay, sorry, first write g of j omega. It is j omega plus 2 and j omega plus 1 at omega equals to 1. This is 2 plus j and 1 plus j, right? And what will be its angle at j1? It is, so we first find the angle of numerator, which is tan inverse of imaginary by real, which is 1 by 2. Okay, and we have to subtract the angle of denominator because, okay, there is, sorry, I lost my internet. Let me reconnect again. Okay, are you able to see my screen?
Yes, ma'am.
Yes, ma'am.
Sorry for the delay. The Wi-Fi was lost. Okay. So have you calculated this angle? So it is tan inverse 1 by 2 minus tan inverse of 1. What it will be?
Minus 18.443.
Okay, so can you tell me the expression explicitly for tan inverse 1 by 2? What is the angle?
.56 degree.
96.56. And what is tan inverse of 1?
26, ma'am. 26.
26. And what is tan inverse of 1?
9
Oh,
26 point.
How much? 45.
ma'am, 45. 45.
Yes. So you will get minus of 18.43.
18.44.
Yes. Find out the ratio of magnitude of the transfer function at omega equals to 10 to that of omega equals to 1 radian per second. So for omega equals to 1 we have already calculated. Calculate for omega equals to 10 and find out the ratio of the magnitude. So our transfer function was j omega plus 2 in terms of omega and j omega plus 1. And if you calculate its magnitude, it is 4 plus omega square divided by omega square plus 1. And then if you do the ratio at 1 and at 10, so at 1 it will be root 5 by root 2, and at 10 this will be under root 104 divided by under root 101. You have to do GW10 divided by GW by 1. So this is under root 104 divided by under root 101, and this one we have already calculated, it was 1.58. So divided by 1.58. How much you will get?
Hmm, 0.64.
Okay, that's the correct option. Okay, let's move to some other problems. Okay, in this problem you have the state space realization where the state space model is given to you, and in this you have the initial condition as 0 obviously, and ut is the step input. You have to find the value of this expression. Sorry, here is t. So limit t tends to infinity. What is the steady state value of under root of x1 square plus x2 square? Try this one. Okay, let's solve this. From the first expression, if you calculate, you will get x1 dot equals to 0. Okay, because the first row is completely 0 and here also this row is 0, so x1 dot is 0. What does it mean? It means x1 minus x0 is 0. Okay, and your initial condition is 0 here, so sx1 is 0. What does it mean? It means that if you plot x1 with t, its derivative is 0, means x1 is going to be constant. Constant means it will remain at the same value from where it started. Okay, and we have the initial condition as 0, so x1 will remain 0 for all time. Is it clear to you? So x1 will be 0 for all time.
x0 or x1?
This I am calculating for x1. x1 of 0 means initial condition of x1 by this term, and it is given that it is 0. Okay, from here also you can say x1 equals to 0. Now what we can write about x2? So let's calculate for x2. x2 dot is minus 9 of x2 plus 45 of ut, correct? And if you do its Laplace transform by keeping initial condition as 0, you will get sx2 equals to minus 9x2 plus 45 of ut, u of s, right? Try to find out x2 by u, that is the transfer function. What you will get? So
45 by 14.
45 by s plus 9.
okay, so you have 45 u of s, and if you do x2 by u, you will get 45
S,
divided by s
S
plus
plus
9. Now can you apply the final value theorem here? You have u given as step input, which is 1 by s. Find x2 as t tends to infinity is equivalent to finding s into x2 as s tends to 0. Am I right? Okay. Now this
Yes,
is
ma'am.
equivalent to, what is x2 from here? It is x2 equals to u, in u is 1 by s, so 45 into 1 by s divided by s plus 9. So you can put here it is equal to limit s tends to 0, s into 45 into 1 by s divided by s plus 9. This will cancel out. We will have s by s plus 9, and s is equal to 0 means 45 by 9. Okay.
Yes, ma'am.
Ma'am, please explain the calculation for x1 dot.
For x1 dot, this one. So
Yes,
for x1 dot equals to 0, what does it mean? You are not going to change with respect to time. Your change with time is 0. Okay, so you will remain
Yes.
from where you have started, and from where you have started at 0. Okay, so for all
Yes.
time you will remain at 0. What does it mean? So even if you go at t tends to infinity, you will remain at 0. Okay,
Yes. Yes.
so that's what we have. if if this expression was not 0, then you will get x1 something. Okay, but here we have x1 0 is 0. Okay, now what we have to find? We have to find this value, which is under root of x1 square plus x2 square.
I mean, x1 dot, the first equation you write this circle, you make the circle. This is what x1 or x0.
Initial condition of x1. It is this
Okay,
one.
okay. Yes.
Okay,
Yes, ma'am.
now since this x1 is always 0, so it is 45 by 9 whole square, which is the same as 45 by 9. And what is the answer then? It is 5. 45 by 9 is 5, right? So the answer for this question is 5. It is clear? If you have any doubt, you can ask. Okay. So for such problems, you just write expression for x1 dot, x2 dot, apply the Laplace transform, and then apply the final value theorem. Clear?
Okay, ma'am.
Yes, ma'am.
Okay. So in another question, we have a linear system, and it is represented by two sets of state equations. So the first set of state equation is x dot equals to ax plus bu, and the another set is w dot equals to cw plus du. So these two sets of equations are used to represent the same linear system. Okay, and it is given that the eigenvalues of the representations are lambda. So these are the set of eigenvalues for this representation. So let me call it 1. So this set of eigenvalues is for representation 1, and this set of eigenvalue is for the representation 2, which is this one. Okay, and you have to identify the correct statement. Remember that these two set of equations, that is x dot equals to x plus bu and w dot equals to cw plus du, is representing the same linear system. So is it possible to represent a system using two different state space models? Can we do that?
Uh, yes, ma'am.
Yes, because it depends on the states we are taking. So the moment we change the state variables, our state space representation will change. So this is not unique for a system. For any system, you can have infinite number of state space models. But what about transfer function?
Unique. It is one.
Yes, the transfer function is unique. Okay. So if you have fixed the output and input of the system and you calculate its transfer function, you will get that same transfer function if you have fixed the input and output. But for state space model, this is not the case. But the moment you fix the state variables, input and output, you will get the same state space model as well. But here we are not fixing the state variables, because in first set we are taking the state variables as x, and in another set we are taking the state variables as omega or w, we can say. Okay, so we have two different state variables. That's why we are getting two different state space models. Okay, so the option 1 is saying that both the set of eigenvalues will be equal if the state variables are equal. Okay, and in the second option it is saying that the set of eigenvalues will be same if the set of state variables are different. Is it possible? If we have fixed the state variables, let's suppose, then which matrix will remain same? So let's suppose you have x dot equals to ax plus bu, and you have omega dot equals to cw plus du. If x equals to w, which matrix will remain same?
A will be equal to C.
Yes, A will always be equal to C, because the moment we fix the state variables, the relation between the state variables is not going to change. And which matrix tells you the relation between the state variables? It is the state matrix, and the state matrix is A in this case and C in this case. So that means A is equal to C. And the moment these matrices are equal, its eigenvalues will also be equal. So lambda will be equal to mu also. So the option A, I think, is correct, because it is saying that if x equals to w, then the set of eigenvalues will also be equal. Are you convinced with this option?
Yes, ma'am.
Yes. And rest all other options, let's see what they are saying. Second option is saying that set of eigenvalues will be equal and the state variables are not equal. So if x is not equal to omega, then A will not equal to C. And the moment A is not equal to C, this lambda will not be equal to mu. Okay, so option B is not correct. In option C, we have set of eigenvalues are different but x equals to mu. This is also not correct. If x equals to w, we have already checked. A will be equal to C and lambda will be equal to mu. And what about the last option? Is it correct or not?
No, it can be correct. It can be false. There is no certainty.
So we have different state variables. X is not equal to w. Then lambda means A will not be equal to C. If A is not equal to C, what does it mean? Its eigenvalue will also be not equal. So this option is also correct. Okay, so this is the last problem for today's session. You have the open loop transfer function of a DC motor, and the transfer function, the open loop transfer function is 10 divided by 1 plus 10s. Now we are representing the open loop transfer function of a DC motor. Can you identify the input and output? What is the output
WS,
and what is WS for DC motor?
uh, angular position of shaft.
Angular velocity it is.
Okay.
We have omega, which is the angular velocity, and what is the input?
RS.
Uh, Input is VA, which is the armature voltage. So when you read about DC motor, you will get the expression in terms of differential equation for omega and input as armature voltage. There you will find that there you can see that you can transform that into state space or transfer function model also. So anyway, we have this DC motor transfer function, open loop transfer function. It is connected in feedback, negative feedback we have. You have to approximate the value of gain Ka that will reduce the time constant of the closed loop system by 100 times as compared to that of the open loop system. Okay, so you have to first identify the time constant of open loop system and the time constant of closed loop system, and then you have to reduce it by 100 times and then calculate the value of Ka. Try this one. Okay, are you able to solve it? So let's see. We are given omega by Va, that is the open loop transfer function, and it is given as 10 divided by 1 plus 10s. So what will be the closed loop transfer function? Okay, first tell me what is the time constant of open loop transfer function?
10.
So incoming feedback. Let's system. So our open loop, so this is open loop transfer function of DC motor. And you have to find the open loop transfer function of system. There you will multiply with Ka also. So it is Ka into 10 by 1 plus 10s. Anyway, the time constant will remain same, and that is equals to, because we can uh, compare it with the standard model, which is 1 plus s tau. So tau in this case is 10. Okay, if you compare the denominator. Now calculate the closed loop transfer function of this one. It will be nothing but 10 Ka divided by 10s plus 1 plus 10 Ka. Okay. Okay. What is the time constant in this case? So for that we have to make this constant term 1, then we have to divide by 1 plus 10 Ka, numerator and denominator. So it will be 10 Ka divided by 1 plus 10 Ka. To convert into standard form we are doing it, and this will be 1 plus 10 divided by 1 plus 10 Ka into s. Okay, now what is the time constant? It is 10, this coefficient, which is 10 divided by 1 plus 10 into Ka. And what we are asked? We are asked to reduce the time constant of the closed loop system by 100 times as compared to that of the open loop. So the time constant of closed loop is 1 by 100 times of open loop transfer function. So let's call it time constant open loop, and let's call it as time constant closed loop. What we need to do, we have to time constant of closed loop is equal to 100 times of time constant of open loop. And now we just have to put the expression and calculate. So this equals to 1 by 100 times of, what was the time constant of open loop transfer function? It was 10. Okay, so these will cancel out. We have 100 equals to 1 plus 10 Ka. Now what will be Ka? 99 divided by 10, which is 9.9. Okay, and in option we have no 9.9, so which option we can choose? The
10
closest one?
C.
C. Yes, we have 9.9, not 0.99, so we have S10. Okay, so that's all for today from my side. If you have any doubt you can ask.
Ma'am, how you equate time constant to closed loop?
I first calculated the closed loop transfer function, which is
Yes,
equal
ma'am.
to this expression. Okay, and now in standard form we know that we don't care about numerator, but denominator should have the form 1 plus s tau, where tau is your time constant. But here we have these terms are constant, these terms are constant, but this is not equal to 1. So we need to make it 1. And how can we make it 1? We can divide numerator and denominator by this value. So I have divided the numerator with this value, and I have divided the denominator. So it is 10s divided by this value, and if you divide this by this value you will get 1. Okay, now you are landed with the standard expression, which is sum numerator divided by 1 plus s into tau. Okay.
Now, ma'am, how this tau is in the next step?
Okay. So this time constant we got, and then we are asked to calculate the value of gain such that the time constant of closed loop equals to 100 times the time constant of open loop. Okay. So just I put the time constant of closed loop equals to 1 by 100 times of the transfer time constant of open loop. So this was the time constant for closed loop. Okay, I just put that value, and then 1 by 100 times of time constant of open loop, which we have already calculated as 10 from here, and then you just have to solve. So these 10 will cancel out, and this is just algebra.
It is not one by 100 time. It is 100 time.
No, it is said, uh, reduce it reduce it by 100 times. We don't have to increase it by 100 times, we have to reduce it. So that's
Clear,
why
ma'am.
it is 1 by 100.
Clear, ma'am.
Okay.
Yes.
So understanding question is very important. So that's how you get little clues on how to proceed with the problem. Okay. Okay, then let's meet next week to solve some problems. I think in next session we will be solving problems on Bode plot and frequency response.
Bye, ma'am.
Okay,
Okay,
thank you,
bye.
ma'am.